All right, properties of ionic compounds. We've already seen how they form and how their bonding works. Let's talk about how that kind of bond reflects in the properties of these compounds, properties of ionic compounds. There we go. So remember, an ionic compound is made when two atoms form an ion. Right? One of the atoms will form what's called a positive ion. Positive ion. Another word for a positive ion is a cation. And that's a word you'll use in your senior chemistry. So it's probably a good idea to get used to that. And then what we have is a positive ion that's going to be joining with a negative ion of some kind. And we saw that they can join in different ways with different numbers of each, but ultimately it's the formation of the ion that makes this happen. A negative ion is also sometimes called an anion. Cations and anions are another way of describing the positive and negative. Okay? And so cat, the prefix cat means positive, and the prefix an means negative. And what holds them together, right? Excuse me, they're held together by the attraction of their opposite charges, right? That's what opposite charges attract. Attraction of their opposite charges. And of course, that is called the electromagnetic force. Now, you don't know much about that yet because you haven't taken your grade 11 and 12 physics. But basically, there are four major forces that control everything that happens in the universe. And the electromagnetic force is one of them. Put in brackets underneath here. That's the force, what it's called. It's the force that causes cation to be attracted to an anion, or a positive charge to be attracted to a negative charge. And it's quite a strong force. It's actually the one major force that influences most of our daily lives, and everything that we do involves this force in some way, shape, or form. And it also, of course, has a very important role to play here in chemistry, in the formation of these ions. Okay? The electromagnetic force of attraction between these two things is very, very strong. That means that this kind of bond is the strongest kind of bond that atoms can make. They really stick together hard. Okay? So let's just add to that ionic bonds are the strongest chemical bonds. The different kinds of bonds that we'll study later, we'll see, are not as strong. They just don't hold together as well because they don't rely as much on this electromagnetic force of two opposite ions. Instead, they're more of a trade-off, where you have two atoms that are kind of sharing their electrons in a way that makes them reasonably happy or stable, but the bond is not quite as strong and they're more easily broken apart. Okay? So the strongest chemical bonds. Because the bonds are so strong, it makes it very difficult for these ions to fall apart. So they're very tough and brittle, right? They tend to be very hard. So maybe I'll put little dashes here for each of the properties. They are the strongest bonds. They make hard, brittle compounds. Brittle means when you try to force it, it crushes into little pieces rather than something that is soft and gooey. Brittle is kind of the opposite of soft and gooey, right? Hard, brittle compounds. Another thing that's interesting about them is that a lot of them will dissolve in water. They all dissolve in water to some degree, right? So do you remember what the word is for dissolving in something? There's a word called soluble, right? So they are they are soluble in water. Water has a very unique chemical structure, and you'll learn more about that later in your grade 11 and 12. I always thought that should be the first thing you learn in grade 9 because it's so important to everything that happens. Almost all of our chemistry happens in water, and that's because water has the ability to sometimes pull apart two ions that are joined together. Water actually has the ability to break this very strong attraction and pull them apart and separate them, and that's how things dissolve. But we can't understand that until we understand more about the other kind of bonding which comes later. So maybe at the end of our unit, we'll be able to understand a little more about how dissolving works. But for today, soluble in water. And we'll just put some more than others. They're not all the same. Some really dissolve really well, and some dissolve just a little wee bit. But they all tend to dissolve somewhat. Okay? And that, again, is because of the fact that they have this ionic bond that water is able to interact with in a sort of a special way. Now, when they are soluble in water, what's interesting is they conduct electricity. Right? If you don't remember what soluble means, you might want to write the word dissolve up there somewhere to remind you, right? When you're making notes, it's important that you don't just write what I write and carry on. You should write little extras when you hear me say things to help remind you when you go to read the notes later. So you might want to scratch in the side there that soluble is the word we use for when something dissolves, right? It's kind of, when you're making your notes, you get into the habit of just copying instead of actually transcribing, which means listening to my voice just as much as the words you see on the board and adding things in that I say, because you're not going to remember that later on. I'm just kind of writing a template on here, right? You have to fill it in with the things you hear. So they, whoops, let's put a Y there. They conduct electricity, excuse me, when dissolved in water. That's interesting. And you'll learn all about how that works in your high school science ahead of you, in your chemistry classes and things. You will learn all about this. For today, we're just going to acknowledge that it happens, and we can't learn everything at once. So that'll be one of the things we'll learn about later. But what's interesting is when they're not dissolved in water, they are insulators. They don't conduct electricity. Remember, a conductor, right, lets electricity flow, whereas they are insulators. They're good insulators, which means they don't let electricity go. Insulators when not dissolved in water. So those kind of two opposite sort of properties, depending on whether they're in water or not. They also have, because of the fact that we said way up here that they have very strong chemical bonds, I don't know how much you know about melting and boiling, right? But essentially what melting and boiling mean is that the molecules or the atoms have to be sort of loosened up, okay? Let me show you very briefly what that could mean. So if you take something like a compound, let's do an example. So maybe I'll write the property first. They have high melting and boiling points. Okay, you know what that means? That means the point where they would turn to liquid or turn into a gas, right? So if we take an example of a compound, a very common one, NaCl, sodium chloride, right? Sodium chloride. This is a good example because this is basically what we call table salt. Now, what's interesting is all all ionic compounds are called salts. In chemistry, we use the word salt to mean any kind of ionic compound. But in our real lives, we use the word salt to describe only this one. See? Real life is not the same as science sometimes. So we call this salt, but when you hear the word salt in chemistry, that implies any ionic compound. It can also be called a salt. Okay? And there's different kinds of salts. Sodium chloride, table salt. Well, if we try to imagine a sodium atom right here, and a chloride atom, right, which is a little bit bigger, right here, and they're attached to each other. Because remember, the chlorine ion is positive, right? It's a plus charge, and the chlorine, which has taken the electron, is a negative charge. So there's one sodium chloride sharing together. So they're very strongly bonded together. Like that, I'll put a little black line. But what happens if another one comes along? Well, what if you have this over here and another one like that, right? With their strong attraction between them. And of course, I'll just put the minus here, put a plus here. Well, you'll notice that the plus here will also be attracted to the minus over here. There will be a new sort of attraction between them. Right? He's attracted to this other fella that he's joined to, but he's also attracted to this guy over here. So when you get a whole bunch of them together, all the pluses are all attracted to all the minuses, and you get sort of something like this. You get, I'm going to try to draw this 3D. I don't know if I can do it actually, but we're going to try. Something like that. And then what happens is, so I'm trying to draw like the top of a cube, right? So then I'm going to go down here and draw like this. And the red ones are slightly bigger. And then I'm going to have a red one over here, but there'll be a blue one sort of in the middle, and then there'll be another red one over here, and then there'll be a blue one sort of in the middle, and then there'll be, and so what you get is this is sort of little, there's a blue one in between every red one. It's actually going to be very difficult for me to draw this 3D. 2D might have been better. We call this, it's like a matrix. It's like, wait a minute. I'm trying to make sure that there's a red and a blue in between every other red and blue. See, so that gets a little tricky because it's also moving back behind. There'd be red ones in behind here and blue ones in between every one. So I'm giving up on trying to make it work 3D here, but something like that. And what happens is there's an attraction between every positive and negative ion, right? Oops, I drew this here. I got it. So all the reds are attracted to all the blues that are nearby it, and all the blues are attracted to all the reds that are nearby it because they're opposite charges, and it forms this sort of cube-shaped crystal. This is called a crystal, right? And they're all evenly spread out and spaced out in there. Now, other things can form crystals too, but they're not the same. Ionic compounds always form crystals. That's why we kind of make it special. They always form crystals like this. Some of the crystals take on a cube shape. Some of the crystals take on different shapes. Like they might form a triangular pyramid kind of shape or different shapes. And we can actually identify, the shape with, or correlate the shape with the compound itself. So forming crystals is yet another property that we'll add to our list in a minute. But what I want you to realize is that this would be a solid, right? This crystal is a solid. Think about salt. This is table salt. When you pour it out, it makes little tiny grains. And those little grains, if you look under a microscope, are actually like little tiny cubes shapes. And they will form these little crystals. Now, if you try to break a crystal, you push on it really hard, it just resists, and then it kind of breaks into little pieces. That's why it's brittle, right? But it takes a lot of force to do that because these bonds are very strong. If you want to melt salt, okay, don't confuse melting with dissolving. When you put salt in water, it dissolves. That's not melting. But if you want to melt salt and get liquid salt, what you have to do is you have to apply heat. And if you apply heat to a crystal, remember in grade 9 you learned that all these little particles of matter are jiggling around a little bit. They're all moving. And the more they move, the more heat they have. So if you warm something up, it starts to vibrate and jiggle more vigorously. And if you start to jiggle these things a lot, some of the jiggling will cause some of the attractive bonds to start to break. And the crystal will slowly break down into smaller bits. And that's called melting. So melting is when the crystal breaks down into smaller bits. But in order to do that, you have to jiggle a lot because you've got to break these strong ionic bonds. And so the high melting point means that you've got to apply a heck of a lot of heat to break these crystals down and get them to melt. A lot of heat. Very hard to melt salt. Very difficult. And then to boil salt, to take the liquid salt and boil it would require even more heat, thousands of degrees in many cases, to get salt to turn into a gas. So high melting and boiling points is a property here that has to do with the strong bonds in between these ions. And then I'll go down here and I'll add, since we've already written the word, I'll add that they form crystals as another property. And that's what a crystal is. It's sort of a, well, we could write, it's sort of a solid, a lattice, right, is another word for lattice structure. It's a regular structure. Lattice is that, you know, the stuff that's wood you put on your deck. It's all the wood that's all crisscrossed. Well, it's a pattern, right? Crisscross. Like the lattice on your deck is, it all goes, all the wood goes this way and then more goes this way, and it makes like a screen. Well, that's a pattern. So it's a solid lattice structure. So you could put a pattern up here if you want to remind you what that means, pattern. Okay, good. So those are some of the main properties. Conducting electricity when they're dissolved, but not when they're not dissolved. Hard and brittle, and strong bonds, very strong bonds. Okay, so the last thing would be some examples. So we talked about NaCl, which is called sodium chloride. Let's put examples here. Sodium chloride. And that's what we call table salt, right? That's what we put on our food, and it happens to make it taste better. But there are other kinds of salt that you can eat. Sea salt, right? Everybody talks about sea salt. They say, oh, it's better for you, it's whatever. Well, I don't know if it's any better for you. It's just a different thing. Sea salt is a mixture of compounds. Another compound is potassium chloride, KCl. That's potassium chloride. And that's a very common element of sea salt. Sea salt is a mixture of both of these. So I'll put it's a component of sea salt. Now, one of the things that scientists and doctors in medicine are studying is the effects of sodium, remember, sodium, on your blood pressure and your body. And there's some evidence that suggests that too much sodium might be bad for you. And so if you eat potassium chloride on your potato chips instead of sodium chloride, you won't get as much sodium. So that's one of the reasons why they say that sea salts and different kinds of salts might be healthier, so to speak, Of course, you got to be careful not to get too much potassium either, right? The funny thing about healthy is just about anything can be healthy, but it's all about balance, isn't it? It's all about levels and how much. There's another salt called calcium chloride. Now watch this one. It has a little 2. That's because if you go through the process and you crisscross, that's how it comes out, right? Calcium is a 2+ ion. So that 2 slides down there, the one from, so you get that one. That's common compound. I'm not going to write the names of everyone here. Well, I guess I will. Calcium chloride. This one is what we call road salt. This is the kind of salt we put on our roads to melt the ice in the winter. When you dissolve salt in something, it changes its boiling and melting points. So if we put salt on the road, the solid ice changes its melting point to a lower temperature. It stays liquid in the cold. Instead of forming ice on the road, it stays as water, which isn't as slippery, of course, and it runs away and all the rest. So we use road salt, right? But any ionic compound is called a salt. The word salt in chemistry means all of them. And there are lots of them. As well, we wrote down a list of about 42 of them, right? Lots of different salts with lots of different meanings or purposes or whatever we want to use them for. We often will find salts as a way to get certain components that we need for health, like vitamins and minerals especially, right? If you need to eat potassium because you're low on it, and you might take a pill, and that pill might contain potassium chloride or potassium sulfate or some other compound that has potassium in it. So we often see ionic salts in things like that and so on. And that's really the gist of it. So there we go. We have the properties of these things, very strong bonds, the strongest bonds that atoms can make, and the result of that are all these properties, and we'll call that a day.